These are the notes for AP Calculus on the topic of limits at infinity, which is directly related to horizontal asymptotes. So limits at infinity refer to if you have a limit and x is either approaching positive infinity or if x is approaching negative infinity. So let's start with the positive infinity case. This means the value, or y value, the function approaches as x increases without bound. In other words, as far right on the graph as you can go. So let's look graphically at some of the different possible things that can happen. So the graph could keep going up forever, in which case your limit would be positive infinity. It could head down forever, in which case your limit would be negative infinity. Or it could approach a specific x value. Sorry, specific y value, I should say. Could be anywhere. And then it could approach it from above or below, or actually could even cross it, but it get closer and closer to it. So if it approaches a specific value, that constant would just be c, so that would be the limit. And when you get a limit that's a specific constant that's not infinity or negative infinity, that's what indicates you have a horizontal asymptote of y equals that constant, c. And then as x approaches negative infinity, that's the y value. The function approaches x as x decreases without bound. In other words, as far left on the graph as you can go. And you have the same possibilities. The graph could keep going up forever, giving you positive infinity. It could head down forever, giving you negative infinity. Or again, it could approach some specific value that could be the same as the infinity side, but not necessarily. It just depends on the function there, where you approach a specific constant that's not infinite, in which case your limit would be that constant. And again, when you get a constant, that's what would indicate you have a horizontal asymptote of y equals c on the left side of the graph. Then there's one other possibility that can happen on either side. Sometimes the graph just stops and doesn't keep going, like with a logarithmic graph or an even root graph where you get imaginary numbers. So if the graph never goes, if x can't go to infinity, you can also get does not exist. Or if the graph never goes to the left forever, if you can't substitute in negative infinity, you can also get does not exist on the left for the limit as x approaches negative infinity. All right, now if you have the graph, you can easily tell, like we went over earlier in the chapter, which of these limits are equal to by just looking at what's happening out in the far right and the far left. But what we're going to look at today is how we can figure out these limits without having the graph, by just looking at the equation. Because a lot of times you'll get equations that you don't easily recognize what their graph is going to look like. So to find these limits, we're actually going to do the same technique to start out with that we do for other limits, where x is approaching a specific constant, except now we're going to substitute an infinity or negative infinity, which first usually seems a little bit unusual, but this is an analysis tool that will make it easier to figure out what this limit is actually going to equal. So we're plugging in, substituting, notice, and x is approaching negative infinity for all the x's. And then notice on the denominator, there's a negative on the outside. That's like a negative 1 there. That doesn't get squared, just the negative infinity. Like that. Now, to help us figure out what this is, because right now we're substituting this negative infinity for all these x's, it's not easy to tell what it is. Just focus on the numerator and the denominator separately. So let's focus on the numerator first. Notice we've got negative infinity to the fifth. That means 5 negative infinities multiplied together, and then negative infinity squared, 2 negative infinities multiplied, and then plus 3. So notice in terms of size and magnitude, whether positive or negative, you can see the squared and to the fifth power negative infinity are so much bigger than the plus 3. That plus 3, in terms of our limit, is basically negligible. It has no effect whatsoever on the limit. It could be plus 100, it still wouldn't have an effect. It would be so small compared to these values. And even though negative infinity squared gives you this huge number, because we've got negative infinity to the fifth here, that's multiplied by 3 more negative infinities in terms of magnitude of size. Even the negative infinity squared, which is tied with that -2 coefficient out in front, is also negligible. So really all that's going to matter in these polynomial functions is the term with the highest exponent. So in the numerator, we just have negative infinity to the fifth, and since it's an odd exponent, when we simplify it, that's going to make it negative. And then on the denominator, same thing. We've got negative infinity times 4, but negative infinity squared. So the higher exponent, that's going to be much larger in size than this one. So this 4 times negative infinity is also negligible in terms of figuring out what the limit is. So all that's going to be left on the denominator, we've got this negative on the outside. And then negative infinity squared, it's an even exponent, so that's going to get rid of that negative. So because it gets rid of it, it won't cancel that negative out. But now the negatives can cancel out, and you can see 2 of these infinities cancel out, leaving you with just 3. So all that's left on the numerator is infinity cubed. And infinity cubed is, notice, it's just when you have infinities left on the numerator, you really only have 2 possibilities, either positive infinity or negative infinity, a really huge positive number or a really huge negative number. In this case, the negatives canceled out, so it's positive. So this one would just be infinity. So that's basically telling us as x goes to negative infinity, the graph on the left side is going up to positive infinity. No horizontal asymptote on this one. What we're going to do is every time we do get a horizontal asymptote, I'm going to write down what it is. But this one didn't have one because we didn't get a specific constant. We got an infinite answer. Now let's look at the same function. Now that we know this shortcut, it can make it a little easier. Where the polynomials, you just focus on the term with the highest exponent. This is the same function, but with positive infinity. So we can focus on the same terms. The x to the fifth is going to matter more than the x squared and the 3, the term with the highest exponent. So infinity to the fifth. And on the denominator, we still have this negative. The coefficients can still affect the answer of the term. So the x squared is a higher exponent than x to the first. So this negative and then infinity squared. So again, subtracting the exponents, we're left with 3 infinity to the third, I should say, on the numerator. But this time, notice there's that negative one that doesn't cancel out. It's left on the denominator. So that's going to give you a huge negative number divided by -1 makes it negative infinity. So this time what it's showing us is as x approaches positive infinity, the graph, the y value approaches negative infinity. So it looks something like that. You don't have to sketch the graph of these. I'm just doing so you can see how this connects with what the graph looks like. All right, let's take a look at the next one. Now, it's not quite a polynomial because of the square root, but we can apply the same principle because it's like a polynomial inside the square root. So with negative infinity, got to be a little careful when you're simplifying. The 5 is negligible compared to the x squared with a higher exponent. So we've got the square root of negative infinity squared. It's going to matter on the numerator. And on the denominator, notice the term with the highest exponent is x to the first versus the -4, so it's going to be 3 times negative infinity. Now, here's where you got to be a little careful in simplifying here. It's tempting to just cancel out the square root and the squared and get negative infinity, but that would actually be incorrect. The correct process to simplify is to first square this. Negative infinity squared, notice since it's an even exponent, would give you positive, and then it'd be infinity squared. And the denominator, we can just bring this as like a -1 times the 3, just like you would with an x, except it's infinity, so -3 out in front times infinity. And then you can simplify the square root of infinity squared, just gives you infinity. Over -3 infinity. This time, notice what happens though, is the infinities completely cancel out. So when that happens, what you're left with is just a constant. So we just have 1 over -3, so -1/3. That's our limit. And what that shows us is as x goes to negative infinity over here, we've got a horizontal asymptote that's going to either come from below or from above. We've got a horizontal asymptote, I'll just abbreviate it HA, of y equals negative 1/3. So just keep in mind, every time you get a specific number here that's not infinite, infinity, or negative infinity, that indicates a horizontal asymptote. Now let's go back to why this wouldn't simplify to just be negative infinity squared. Besides the way I squared it and took the square root, the other way to see that is this square root right here is what's called the principal root. It's like the square root button on your calculator. And if you ever take the square root of something on your calculator, you may or may not have noticed it will never give you a negative number. It's a function. Notice there's no plus or minus here. That's only when you take the square root of both sides yourself. So because of that, it's only going to give you the positive root of it. So there's no way that a square root like this could give you a negative answer, including negative infinity. That's another way to see why this must simplify to be positive infinity on the numerator. All right, let's take a look at the same function for positive infinity. So here, the same terms with the highest exponents matter. So the square root of infinity squared and 3 times infinity on the number. This one's a little easier to simplify here. Right away, that just simplifies to be infinity over 3 infinity. So again, when all the infinities completely cancel out when they have the same exponent in the numerator and denominator, then we're left with just the constant that's left. 1's left on the numerator, so 1/3. So that's our limit. And again, when you get a specific value, in this case, as x approaches positive infinity on the right side, that would mean the graph would either approach from above or below, like that, and we'd have a horizontal asymptote of y equals 1/3. So this one happens to have 2 different horizontal asymptotes. Sometimes these can be the same, but sometimes, as we see right here, sometimes they're different. All right, let's take a look at some other examples now. Again, all these polynomials, we can use that same shortcut. As x approaches infinity, the highest exponent is a 2 on the numerator. It would be 4 infinity squared. And the denominator would be negative 5 infinity cubed. Notice this time, unlike the first problem, 2 of them cancel out and we're left with infinity on the denominator. So when this is the case, think about what this is here. We've got 4 divided by some huge negative number because of the negative 5 there, times infinity. So what that gets really, really close to, when you have infinities left on the denominator, it's really, really close to 0. And that's, remember, limits don't have to actually equal, it's just what it's getting closer and closer to. So as you go to infinity, this gets really, really close to 0. So that would be your limit. So what this would look like, as x approaches positive infinity, it's right on the x-axis here. We have a horizontal asymptote of y equals 0. So we got a specific value. All right, let's take a look at the next one here. As x approaches negative infinity, we've got the highest exponent is 4 on the numerator, so it would be 3, negative infinity to the 4th, and the denominator, the highest exponent is the 4, so negative 2, negative infinity to the 4th. So you could raise these both to the 4th, or you could recognize, well, they're just going to cancel out entirely, leaving you with just negative 3s. So that's your limit, and again, we got a specific value there. So that's going to be a horizontal asymptote as x goes to negative infinity So on the left side of the graph, you're going to have a horizontal asymptote of y equals negative 3x. Again, when you're doing your homework, you don't have to draw these out. This is just to help you visualize what's happening on the graph. All right, now let's take a look at some with radicals involved in fractional exponents. So you can apply the same principles, but you just got to be a little careful, especially with negative infinity. So let's start with an easy one with positive infinity. This one we can do just like the other ones. So now this is 4/7. This is 1/2. We rewrite it in fractional exponent form. So 4/7 is a little bigger than 1/2. So that's the term that's going to matter here. 4 infinity to the 4/7. And then on the denominator, 3/4 is bigger than 1/3, so that's the term that's going to matter, including the negative. So negative infinity to the 3/4. Now here to simplify, since they're fractions, remember we subtracted the exponents, but in order to subtract with fractional exponents, you need a common denominator. In this case, that would be 28. So this would be 4 infinity. When you multiply by 4/4, that's 16/28. And multiply by 7, that's 21/28. So when you subtract, these cancel out, and you're left with 15/28. So we have 4 on the numerator divided by negative infinity. Sorry, not 15, 5. 5/28. And again, notice we've got infinities left on the denominator. So that's going to be approaching just like this one, 0. All right, so this tells us we've got another horizontal asymptote as x approaches infinity. Right on the x-axis again. So we've got horizontal asymptote of y equals 0. All right, now be careful with negative infinity. You might think we're going to use the exact same process, and we would, except notice we've got an even root here, that's a square root, and an even root here, that's a fourth root. So because of that, remember you can't have negative numbers inside of even roots. These two are fine because they're odd roots, a seventh root and a cube root. So that means those are imaginary. And that means if it's imaginary, it actually can't even plug in negative infinity here. There's nothing over there on the graph. So this would be a case where it does not exist. So it never approaches negative. There's nothing on the far left of the graph. All right. Let's take a look at another one here. This one with fractional exponents. This one with negative infinity. But notice, unlike the last one, cube root, fifth root, seventh root, they're all odd roots. So this one will not be a does not exist case like the last one. So 2/3 is bigger than 1/3. So we'll substitute that in here. Negative infinity to the 2/3. And on the denominator, we've got 2/5 versus 1/7. 2/5 is bigger, so 3 and infinity to the 2/5. Okay, and again, we've got fractional exponents, so in order to subtract them, we have to get a common number, which in this case, 2/3 and 2/5 would be 15. So I have negative infinity multiplied by 5, that's 10/15. Divided by 3, and negative infinity multiplied by 3 and 3, that's 6/15. And then we subtract this time, we're left with 4/15 on the numerator. So this is 4/15. We basically have this, negative infinity to 4/15 divided by negative 3. So remember we saw when there's infinities left on the denominator, we always end up with 0. However, when infinity is left on the numerator, it's going to be one of two possibilities, either infinity or negative infinity. So the way to tell which one it is actually by switching this back to radical form. So notice the roots are on the bottom, just like a tree, so that's a 15th root of negative infinity to the 4th power. The divided by 3 doesn't really affect the answer, because it's going to be so much larger on the numerator. So this is an odd exponent, right? So an odd exponent of a negative infinity, that would give you a negative answer, but because of this even one, that's what's going to make it positive infinity. So this is saying as x approaches negative infinity, the graph is going up to infinity. Versus if this, let's say, had been 7 here, 7/15 have been left over, then it would have been negative, 15th root would have been negative, and to an odd exponent would have kept it, it would have been negative infinity instead of positive. All right, let's take a look at one with a trig function now. As x approaches infinity, we'll have sine of 3 infinity on the numerator. Oops. And for now on the denominator, let's just draw the whole thing here. Infinity squared minus, because this one's not, doesn't fit our polynomial forms of our other ones, because we've got a trig function in there. So the easiest way to figure out how to handle this is by thinking about the graphs of sine and cosine. So remember the graph of sine. Now notice the 3 will change how often it repeats the period, but it won't change the amplitude. That would be a number out in front. So it still goes between 1 and negative 1. Sine starts here at 0. Just keeps going like that forever. Versus cosine, starts up here at 1, goes to negative 1, keeps repeating forever. But again, the thing they have in common is they both go back and forth between 1 and negative. This one actually isn't. Yeah. Go like that. Okay. So they both fluctuate back and forth between 1 and negative 1. So just think about this. On the denominator, first of all, cosine goes between 1 and negative 1. So it's really, really small compared to infinity squared is huge. So in this case, that's negligible, and infinity squared matters. And then we've got sine of 3 infinity between 1 and negative 1 again versus infinity squared. See how this one's so much larger? So when the denominator is so much larger, just like when we had infinities left on the number, that means this limit's going to equal 0. So that would mean that graphically, as x approaches infinity, we've got a horizontal asymptote. Of y equals 0. Now the next one just is in factored form. These are polynomials, but it's in factored form. So you could multiply it all out and then plug in substituting negative infinity. Or remember what we said, when it's just polynomial, it's the term with the highest exponent that matters. So really that's all you have to multiply out, the highest exponent. So notice on this one, the x squared is the highest exponent and the x is the highest exponent. So that would give you x cubed on the numerator. That's what's going to matter. And in the denominator, we've got a couple things. If you just look at the binomials first, we got 3x and negative x. That's going to produce the highest exponent. That's going to give you negative 3x squared. But then that gets multiplied by the x out in front, giving you negative 3x cubed. And then when you substitute a negative infinity into the ones with the highest exponent, you get negative infinity cubed divided by negative 3 negative infinity cubed. So they have the same exponent, so you can see the infinities completely cancel out, leaving you with negative 1/3. So again, we get a specific number here. So that means this one would have a horizontal asymptote as x approaches negative infinity. Of y equals negative 1/3. All right. Now notice these are not considered polynomials because they have these exponential functions in them. The 2 to the x when the x is up in the exponent, hence the name exponential. So let's look at the same function for both infinity and negative infinity. Start with infinity. So let's substitute in the whole thing to see if we can tell what's going to matter. So we've got 3 minus 2 to the infinity on the numerator divided by 5 plus 2 to the infinity in the denominator. Well, notice the 2 to the infinity, that's like 2 times 2 times 2 times 2 times 2 forever, compared with 3. So this in size, this is going to be much, much smaller. Same thing here, 2 to the infinity, 2 times 2 times 2 times 2 forever, versus 5. So the terms that are going to matter are negative 2 to the infinity divided by 2 to the infinity. And you can see those completely cancel out, leaving you with just negative 1. So this one would have a horizontal asymptote as x approaches infinity of negative 1. Y equals negative 1. Now be careful though, it's tempting to think that because these mattered with positive infinity, they're going to definitely be the ones that matter with negative infinity. Let's see if that's the case or not. With polynomials you can do that, but this is not a polynomial. So 3 minus 2 to the negative infinity divided by 5 plus 2 to the negative infinity. Well, here it's easier to analyze if those were not negative exponents. But be careful, you can't move this 2 to the negative infinity to the denominator because this is not in factor form. We've got this other term 3 here. So what you can do, though, is just rewrite it on the numerator. Instead of 2 to the negative infinity, that's the same as 1 over 2 to the infinity, making it a positive exponent. And the same thing on the denominator. 5 plus 1 over 2 to the infinity. So notice 1 over 2 to the infinity, see it's got infinities on the denominator. So that's basically 0. And now 3 is much bigger than 0, and so is 5. So what ends up mattering is the 3/5. So that ends up being your limit here. So this one would have another horizontal asymptote on the left side. It'd be y equals 3/5. All right, let's just take a look at a few more here. Let's look at another trig function one that's a little different. So it's got a 1 over x inside there, so it'd be cosine of 1 over infinity. But again, we just saw 1 over some huge number there. That's really close to 0, so that becomes cosine of 0. And if you draw that out here, here's 0. Here, cosine, remember, is the x-coordinate, which is 1. So this would be 1, and we've got a specific value, and that would indicate as x approaches infinity, we've got a horizontal asymptote of y equals 1. All right, now let's look at ones that are mixes, a little more polynomials versus exponentials. This one happens to be e to the x instead of like the other one was 2 to the x. Remember, e is about 2.71. So when you substitute infinity on the numerator, it's just a polynomial. So you can see the infinity to the 10th is going to matter more than the infinity squared, the one with the highest exponent. So infinity to the 10th. And then we've got e to the infinity. So the question is, we can't simplify anything there. Which of those is going to be larger? If the numerator is larger, that means our answer is going to be infinity because there's no negatives here. If the denominator is larger, that means our answer is going to be 0. So as we head off to infinity, this one initially starts out bigger because it's infinity times infinity times infinity, 10 infinities multiplied together. But this one actually ends up being bigger. Exponential ones, as long as the base is bigger than 1, in the long run, it's e times e times e times e forever. These end up being larger and will overtake this one. So because of that, we end up getting 0. So this would have a horizontal asymptote of y equals 0 right on the x-axis. Now let's see if the same thing happens with negative infinity. Well, with negative infinity, it would be negative infinity to the 10th is going to matter on the numerator. And this time, notice it's e to the negative infinity on the denominator. So this one, let's simplify so we don't have to deal with that negative exponent and the negative here. Well, it's an even exponent here, so that's going to be positive infinity to the 10th. And this is the only term here, so we can actually move that up and make it a positive exponent. So times e to the infinity. So here we've got a huge number times another huge number. There's no negatives involved, so this would just be infinity. There's nothing left on the denominator. And because we got an infinite answer, no horizontal asymptotes here. Finally, let's look at how we handle a piecewise function. It's not really that much different, it's just you have to make sure you use the correct piece. And it's worded a little differently. It says find all the horizontal asymptotes. And remember, horizontal asymptotes come from one of two places. Either the limit as x approaches infinity on the right side, or the limit as x approaches negative infinity. Remember, we saw, like on the second problem here, that this one actually ended up having two different horizontal asymptotes, one as x approaches negative infinity and one as x approaches infinity. So whenever you're asked to find all the horizontal asymptotes, that means you need to find both the limit as x approaches infinity and the limit as x approaches negative infinity. If you only do one, you risk the chance of not finding all the horizontal asymptotes and only finding some of them. So let's say we start with infinity. Well, limit as x approaches infinity of f of x, you can just abbreviate it here. Just think which one would make sense to use for infinity. Well, infinity is greater than 0, so you use this piece. So on the numerator, you'd have 2 to the infinity. And the denominator, notice the minus 1 is negligible compared to the size of the 3 infinity. But unlike that other one, these don't have the same base, so you can't just cancel them out. So you just have to think which one is larger. If the 2 to the infinity is larger, it's going to be infinity. If the 3 to the infinity is larger, is 0. And you can see this is 3 times 3 times 3 forever versus 2 times 2 times 2 forever. So this one's larger, meaning our answer is 0. And since we got a specific value, that means this one has a horizontal asymptote of y equals 0 on the right side. So again, you don't have to sketch a graph, but this is what it would look like roughly on the right side. Oops. Okay, and then let's also find the limit as x approaches negative infinity. But for negative infinity, let's see which piece would make sense to use. Well, for negative infinity, it's not greater than 0, it's not between negative 3 and 0, it's less than negative 3, so you have to use this piece. And it's a polynomial, so you can use the highest exponents. So it'd be 2 negative infinity squared divided by the denominator infinity squared, or negative infinity squared, I should say. So notice they completely cancel out here. And we're just left with 2 over 1, which is 2. So that means, since we got another specific value, we have another horizontal asymptote of y equals 2. So this one happened to have 2 different horizontal asymptotes. And that's the most you can have, because you only have 2 different sides, infinity and negative infinity, of your function. And that concludes the notes for AP Calculus on the topic of limits at infinity and horizontal asymptotes.